Alright, integrals chapter 1, day number 1, fundamental theorem of calculus, parts 1 and 2, and basic integral notation. Alright, so let's let y equal f of x be a function which is non-negative and continuous on a to b, where a is less than b. Let a denote the area under the curve y equals f of x and above the x-axis between a and b. So that area can be calculated by using a couple different methods. One, we can use Riemann sums. We can use Riemann sums by calculating the area of a bunch of rectangles. Okay, now this will be an estimate. Won't be perfect. Or two, we could use the integral from a to b of f of x dx, which will get us an exact area under that curve. Now there's 4 different ways to do a Riemann sum. I'm going to talk about that on the next page. But fundamentally, we're going to use the area under the curve using the integral notation. Alright, so here is a breakdown of the Riemann sum. Okay. What the Riemann sum is basically breaking this area under this curve, as you can see in this second diagram, into a bunch of rectangles. It looks here like they're using the midpoint method, as that point right there is the midpoint of a rectangle. So what's done is take the base times the height, which is just a y value. Alright, so you take a height and a base and you multiply them together, and you basically break up this interval into n subintervals, and then you can find an approximate area under that curve. So Riemann sums. So method 1 is a left-hand sum. Method 2, right-hand sum. Method 3, midpoint. And method 4 is the trapezoid. The trapezoid tends to be, depending on how wide your intervals are, tends to be the most accurate. But depending on the function, it's not necessarily always true. So let's move on to some integral notation and properties of integrals. Okay, so as we talked about earlier, the area under the curve from a to b, labeled as capital A, is the integral from a to b of f of x dx. That is if f of x is always greater than or equal to 0. Okay, so the integral if f of x is less than 0, the area under that curve will be negative. Okay, it will be negative unless we decide to work differently and talking contextually, like, say, for example, particle motion problem, where we want to know the total distance traveled, then we don't want a negative distance. One of the properties of integrals is if we change the direction, right? See how I have from a to b of f of x, that'll be equal to the opposite of the integral that's flipped in order. Alright, so just a handy property to have in your back pocket. Okay, now something interesting and helpful, especially when we, like I said, get to particle motion. Let's say the area under the curve here is 10, here is negative 12, and here is 8. Okay, so if I wanted the area under the curve from a to b of f of x dx, I would have 10 minus 12 plus 8, which would be 6, which would be the displacement, right? This would be the, when I'm talking about motion, this would be the total displacement. Where does the particle or the object end up after that amount of time? Now, if we wanted to know the total distance traveled, we would take the absolute value, which then changes that from a negative 12 to a positive 12, which gives us a total distance traveled of 30. So there's some overlapping work going on there. Just a property of integrals to be aware of. This is about, right here, this property is about as clear as it gets. The integral from a to itself of f of x, right, would be this, just that area there, which has no width, therefore it would be 0. Another property that's pretty nice to work with here and can be helpful, especially with the fundamental theorem, like you'll see in a minute, is the integral from a to b of f of x is actually the sum of two integrals. So we can just find some value c in between them and split it up into two separate integrals from a to c and then from c to b. If it bothers you that c is between a and b, it bothers me too. So yeah, just deal with it. Alright, and then the integral of some sum of two functions can be split into two integrals. The integral of each function and the sum or difference of both of those. Alright, let's keep moving. This is called the average value. Alright, and what the average value is if I take the integral of f of x, right, finds me the area under the curve, and then I take the average of that area, what that does is it finds the average value of that function on that interval. Alright, and that's especially useful, like I said, on any sort of particle motion, any sort of water tank type problem, or like you may have seen on the AB exam last year, the escalator problem. It would have given you the average number of people in line at any given time, that sort of thing. So you just use this formula, right? And what that's going to find is some c value. Right? So here's two c values here and really close to 0. We'll call that c2 and c1, where the function hits its average value. Okay, and that's just an estimation. I don't know exactly where it would be, but somewhere in there, right, where it would have this value f of c, which is the average value. That's pretty much applicable to any situation where there's an oscillation of sorts, and it would make sense in the given problem. The escalator problem would probably be a good one where they could have used that. Okay, proof here of the average value. Not going to go over that. You can look at it on your own time. Okay, I'd like to look at the fundamental theorem of calculus part 1. If f is continuous on the closed interval a to b with a less than b, then the function f of x equals the integral from a to x. This is a constant, this is a variable, of f of t dt is continuous on a to b, and f prime of x is f of x. So what the heck is that saying, double lightsabers? It's saying this: the derivative of an integral is that function with that variable plugged in. That's it. How does that work? And what the heck happens to this? Well, let's take an example. Let's take d dx of the integral from, let's say, 2 to x of t squared dt. Okay, so that would be equivalent to the derivative of that evaluated integral, right? So let's evaluate that integral. So what would be the integral of t squared dt? Well, it'd be t cubed over 3 evaluated from 2 to x. Okay, so let's rewrite, simplifying. That would be x cubed over 3 minus 2 cubed, which is 8 over 3. What happens when I take the derivative of x cubed over 3? Well, when I take the derivative of x cubed over 3, I get 3x squared over 3, which conveniently is equal to x squared. And what's the derivative of a constant? Nothing. Therefore, the derivative with respect to x of the integral from 2 to x of t squared dt is simply this value x plugged in for t. Now there's one thing you need to be careful for. If we have a chain rule possibility here, if I have an integral from 5 to, let's say, x squared of, I don't know, t squared dt, then not only are we going to have x squared plugged into that t squared, right, which would be x to the 4th, but we also have to multiply by the derivative of that thing. Okay, so in this case, what's the derivative of x? Well, it's 1, so it's really there, it's just hidden. Okay, that's the fundamental theorem of calculus, part 1. The fundamental theorem of calculus, part 2, is actually what we used in part 1. If I take the integral from a to b of f of x dx, that's going to be equal to the antiderivative evaluated at a and b, and then their difference. So it's f of b minus f of a. This is the big thing right here. Right? We evaluate at these limits and take their difference of the upper minus the lower. Okay, so let's use the fundamental theorem part 1 to do these problems. Okay, so part A, if I'm taking the derivative of this thing, remember what we just said, we're going to plug in that variable right here. So I get cosine cubed of x times its derivative, which of course is 1. We would be done. There is f prime of x. Okay, how about on this one? Well, in order to do the fundamental theorem, we need to alter the limits of integration here so that the variable is on bottom, or on top, and the constant is on bottom. But if I do that, I got to make it negative, right? I got to change this sign. Therefore, what I get is e to the x squared times 2x. Remember chain rule here, right? If the derivative of that is something other than 1, then we got to go with it. All right, so then I get negative, how about negative 2x e to the x squared? That would be f prime of x. Ooh, how about this one? Using properties, I'm going to turn f of x into two functions. Check it out. I'm going to go from x to some value a of 1 over t squared plus 3 dt plus the integral from a to x squared 1 over t squared plus 3 dt. Alright, so another thing I got to do here is I got to flip these limits. That makes that opposite. Alright, so now we go. So the derivative, notice that here in this piece I will not have chain rule involved. So the derivative of that piece would be negative 1 over x squared plus 3. And the derivative over here will involve chain rule. So it'll be 1 over x to the 4th plus 3 times the derivative of that, which is 2x. I would leave it just like that. I would call f prime of x that thing. I wouldn't try to simplify it. You don't need to. Okay, it doesn't require you to go any further than that. All right, let's look at this problem here. Let y equal f of t. Okay, so what we're going to be doing here for g of x is we're going to be accumulating some area. So g of 1, what does that exactly mean? G of 1 means from 0 to 1 of f of t dt. So let's go from 0 to 1. That would be this area here, which is a trapezoid. Okay, now you just use your geometry skills, which hopefully you haven't totally lost. And that would be the area of a trapezoid, which is 1/2 base plus base times height. Height is going to be 1, the distance between the two bases. And the two bases are 1 and 3. So it looks like g of 1 equals 2. Why don't you take a couple minutes and try to find b. So I evaluated those integrals by splitting it up from 0 to 2. That would have given me this area. And then from 2 to 3, which gave me that area, I added them up, got 6 plus pi over 4. Alright, so part C is a little weird, right? It's a little different. Let me erase this, give myself some space. Okay, so part C is weird because it asks for the derivative. Well, what's the derivative of an integral? Right, so let's just evaluate as we know. Go through part C and see what that means. Alright, clean that up. There we go. So what would, if g of x equals this, what would g prime equal? Well, g prime would be fundamental theorem of calculus, right? Would just be f of x. So g prime of 1 is just going to be f of 1. What is f of 1? F of 1 is 3. So g prime of 1 equals 3. How about g prime of 3? G prime of 3 would be f of 3. F of 3 equals 1, therefore g prime of 3 equals 1. Okay, how about g double prime of 3? Well, g double prime of x, hold on, let's redo this. How about g prime of x? G prime of x equals f of x. So g double prime of x would equal the derivative of f of x. So that just means the slope of f of x at a given point. Well, what's g prime of 3? G double prime of 3 is f prime of 3, which there, the slope of the tangent line there would be 0. So g double prime of 3 is equal to f prime of 3, and therefore would equal 0. So get my answers here. It's all good. Fundamental theorem of calculus. That's it for day number 1 of integrals. We'll see you tomorrow.